was the introduction. Hello everyone, I'm Jiacheng from Shanghai Jiao University. I'm going to present a hardware-software co-design for efficient secure containers. Containers are widely used in the cloud for building and deploying applications, owing to their portability and scalability. A traditional container architecture runs multiple containers on a shared OS kernel. While it is lightweight and efficient, the isolation between the containers is weak due to the vulnerabilities in the large shared kernel. In contrast, secure containers, such as kata containers or gvisor, run each container on a private guest kernel for stronger isolation. Compromising a single guest kernel does not affect other containers or the host kernel. Recently, there is a growing demand for building private clouds based on an infrastructure as a service cloud. In such a nested cloud, containers are deployed in a VM instance leased from the IaaS cloud. For example, 36% of Alibaba secure container users use virtualized instances to host their secure containers, and other providers like AWS also offers virtual private cloud services. The benefit of nested cloud is its low cost, the flexibility on management, and the elastic scaling of resources. Running secure containers in this architecture requires nested virtualization. The L0 kernel runs the virtual machine with an L1 kernel, which in turn isolates multiple secure containers. This can be implemented with software or hardware-based virtualization. However, both techniques have some performance issues. When hardware-assisted virtualization, or HVM, is used, the secure container and the L1 kernel are isolated in different VMCS. The L1 kernel relies on the L0 kernel to manage secure containers. When the container triggers the VM exit, it first traps to the L0 kernel, and the L0 kernel resumes the L1 kernel. After handling the exit, the L1 kernel returns to the secure container with a reversed process. This redirection incurs high context switching overhead. Moreover, hardware-based nested virtualization also increases the overhead of memory management. Without hardware support for three-stage address translation, hardware-based virtualization relies on the L0 kernel to manage a shadow page table, shadow EPT for each secure container. Handling one EPT fault in the container requires multiple traps to the L0 kernel. When software-based virtualization, or PVM, is used, the secure containers are isolated without using virtualization hardware. The guest kernel runs inside the user mode, which is CPU ring 3, and isolated from the applications with separate page tables. In this architecture, application system calls should be redirected by the host kernel, and this redirection incurs the overhead of additional page table and the CPU mode switches. PVM also increases the overhead of page fault handling. Without hardware-based EPT, PVM implements two-stage address translation with shadow paging. Handling one page fault inside the application requires multiple traps to the host kernel for redirecting the page fault exception and updating the shadow page table. We observe that the overhead of HVM or PVM stems from a mismatch of privilege levels. The secure container architecture requires three privilege levels. The host kernel isolates multiple guest kernels, and each guest kernel isolates multiple application processes. And the CPU hardware only provides two privilege levels, CPU ring 0 for OS kernel and CPU ring 3 for user applications. There is no dedicated CPU privilege level for guest kernels, so that HVM or PVM have to isolate the guest kernel with virtualization extensions or user mode execution, which results in the performance overheads. So our work aims to create a new privilege level for efficient isolation of secure containers. Based on the previous analysis, we can derive two design implications based on previous analysis. And the first one is that the new level should enforce efficient cross-privilege switches, including efficient system calls, exceptions, and VM exits, without the additional redirection. Second, the new level should enforce memory isolation between the containers without implementing the abstraction of two-stage address translation to avoid the overhead of EPT shadowing or shadow paging. This abstraction is designed to provide an unified physical address space for arbitrary general-purpose virtual machine, but it is not necessary for the security isolation of containers. A recent CPU hardware feature, PKS, provides the opportunity for creating the new privilege level. PKS enforces memory isolation in one kernel address space. It divides the space into 16 isolation domains and uses 4 bits in the page table entry to represent the memory domain ID of a specific page. And it also introduced a new PKRS register to store the read-write permission of each domain. Based on PKS, we propose container kernel isolation, or CKI, a new secure container architecture that implements 3 privilege levels. PKI co-locates the guest kernel and the host kernel in CPU ring 0, which is the kernel mode, and isolates the guest kernel and the host kernel with PKS-based intra-kernel isolation. The applications still run in CPU ring 3, which is the user mode, so that system calls and exceptions can be directly handled by the guest kernel without additional context switches. PKS only provides 16 isolation domains, while one machine may host hundreds of containers. To overcome this limitation, we combine address space isolation with PKS isolation. Different containers and the host kernel are isolated in different address spaces, and inside one address space, the guest kernel is deprivileged with PKS isolation. Each guest kernel operates with the security monitor. The guest kernel and the monitor runs inside one address space with different PKS permission. The guest kernel can only perform privileged operations by invoking the predefined interfaces provided by the monitor or the host kernel. This architecture can support an arbitrary number of secure containers with only 2 PKS domains, one for the guest kernel and one for the security monitor. CKI enforces memory isolation between the containers with single-stage address translation. The host kernel allocates contiguous physical memory segments to each secure container, and the container's guest kernel directly manages the page tables that translates guest virtual addresses to host physical addresses without going through the guest physical address layer. The page tables are read-only inside the guest kernel due to PKS isolation. It can only be modified by the security monitor. When the application triggers a page fault, it directly traps into the guest kernel's handler. The handler allocates a new physical memory page for the application, and then invokes the monitor with an efficient PKS gate to update the page table entry, maps the new page to the address space of the application. The security monitor checks that the allocated page falls within the segments allocated to the secure container and then updates the page table entry. After that, the monitor resumes the guest kernel, and the guest kernel resumes the application. This page fault handling process is efficient as it only introduces a small overhead for PKRS switches and simple security checks. CKI also offers a hypercore gate for each secure container to invoke the functionalities in the host kernel, such as sending virtile commands. External interrupts occurs during the secure container's execution are redirected to the handler in the host kernel to avoid denial of service attack. These two kinds of gates are both efficient as they directly switch the context between the guest kernel and the L1 host kernel without trapping to the L0 kernel. While running the guest kernel in CPU ring 0, the kernel mode brings performance benefit. It also incurs a security challenge. PKS only isolates memory, while the guest kernel in ring 0 may escape by running arbitrary privileged instructions. For example, it may change the CR3 register to switch to an arbitrary page table, or run the CLI instruction to block interrupts for denial of service. Therefore, CK have to isolate these instructions from the guest kernel. This challenge has not been fully solved by previous work without using virtualization hardware. CK proposes a lightweight hardware feature on PKS for instruction isolation. It relies on the PKRS value to identify the current privilege level. The PKRS value is non-zero when the guest kernel executes, which represents the limited memory view, as we use PKRS for memory isolation. While the monitor and the host kernel executes, the PKRS value is 0, which represents an unlimited memory view. So the extension blocks destructive instructions when PKRS is non-zero, so that running these instructions in the guest kernel will result in an exception. CK also designs other defenses against potential attacks when running guest kernels in ring 0. For example, an attacker may directly jump to the interrupt gate through control flow hijack to inject fake interrupts to the host kernel. For the solution of this attack and other design details, please refer to our paper. We evaluate CKI in a nested cloud scenario and compares it with HVM and PVM using micro benchmarks and application benchmarks. Compared with PVM, CKI could reduce the system call latency by 3.7 times as it avoids additional page table and CPU mode switches. CKI also reduces the page fault latency by 30 times and 4 times compared with HVM and PVM, as it avoids the expensive VM exits for EPT shadowing or shadow paging. Compared with HVM, CKI reduces the hypercore latency by 17 times, as its hypercore no longer needs to trap to the L0 kernel. CKI could reduce the end-to-end latency of memory-intensive applications by up to 47% and 72% compared with PVM and HVM, thanks to the efficient page fault handling process. CKI could also increase the throughput of SQLite bench by up to 24%, as it reduces the system call overhead for file system access. Compared with HVM, CKI increased the throughput of Memcached and Redis by up to 6.8 times and 2.0 times, as it reduced the VM exit overhead for volatile networking. To conclude, container kernel isolation, or CKI, constructs a new privilege level for efficient isolation of secure containers by using and extending a lightweight CPU hardware feature, PKS, for efficient intra-kernel isolation. It outperforms both HVM and PVM in the emerging nested cloud scenario. Thanks for your attention, and I would like to take questions.